So today we're actually on the last week of databases. We're going to be covering physical design today and on Tuesday. And then next Thursday we switch over to scripting languages. And hopefully you got my announcement on Piazza that I've moved the exam till the Tuesday after fall break. So it used to be scheduled for next Thursday. A week from today, it's not next Thursday. It's now Tuesday, October 21st. And I will get a sample exam published so that you can take a look at the way the questions have been written in the past. And probably once I've gotten it written, which will be right before fall break, I'll give you a few pointers about it. But basically it covers everything in database that we have done thus far. And I'll give you a one-page cheat sheet front and back. So it won't be open book, but you will be allowed to use a one-page cheat sheet front and back. You can put anything on it you want. Okay, you can put it in 7-point font if you can read that small. Okay, but you're not allowed to bring a magnifying glass. So that's pretty much the broad outlines of it right now. And pretty much you can be expected, I'll ask you a couple SQL queries. You're going to have to do probably some relational algebra and calculus queries, some normalization, some entity relationship design, and something on physical database design, which we're talking about for the next 2 weeks, or for the next week. Okay, so there's kind of two goals to physical design. The first goal is just mapping relations onto files. And the second is selecting indices that are going to make it more efficient for the query processor to retrieve data from those files. So the first goal is to map relations into files on the file system. And the second goal is to select indices to aid the query processor. The first one, the mapping of relations into files, is going to basically come down to what file organization we choose. And it's going to be either as what we call a heap, which is just an unordered file, or it's going to be as a tree, and specifically we use something called a B tree, or it's going to look like a hash table, except it's going to use something called extendable hash tables rather than the kind you're used to in memory. And we're going to go over B trees and hash tables later today and on Tuesday. We're actually first going to talk about selecting indices to aid the query processor. Before we do that, what I've found in the past is that none of our courses spend a huge amount of time talking about characteristics of disk or file organization on disks. So some of you are very familiar with the way disks are organized, and others, actually it turns out, seem to have not so good of a background. In fact, I will ask, how many of you in one of the courses that you've taken have had a pretty extensive introduction to disks and kind of how they operate? Okay, that's what I'm seeing. John, to your best, you're kind of going like that. So I'm not seeing that many hands. So I am going to, as I say, kind of run through a brief description. So basically, a disk, 3D skills aren't good, but basically disk consists of platters. And the platters are stacked on top of each other. So they look a lot like a stack of dishes. And the platters all rotate. They rotate synchronously, so they can't rotate in different directions. They all rotate together synchronized. And between each pair of platters, there's a read-write head, which is capable of reading or writing data to one of those platters. And the disk is, each of the platters is magnetized. So basically the read-write head is applying some kind of, I guess, electrical force that will cause magnetic changes to occur to the platter, and that's storing the bits. And the platters are further divided into tracks. And as you can see, the tracks do get smaller as you move toward the center of the disk. So actually the outer tracks are capable of holding more data than the inner tracks. So there's a constant density to what can be stored. And we typically talk about dividing further each track into blocks. And blocks are the unit that is read into memory when we read from a disk. So we don't read an entire track, we instead read a block, which on Unix traditionally has been 4096 bytes has been the typical block size for Unix. I'm less familiar with what other operating systems use. So even if you just want to read a tuple that, say, is 50 bytes long, you not only will get that tuple, but you will get, well, if this is 50 bytes, you'll get about 80 other tuples with it that come into memory at the same time, because it's not just going to read the 50 bytes on the block, but it's going to read the entire block. So that's kind of the unit of transfer that you get. Okay, and I know there's also something often called sectors, but we're just going to worry about blocks in this course. So blocks are the unit that gets read into memory. And there's two primary elements that determine access time on a hard disk. So for someone who's had some course that's talked about this before, can you tell me what one of the two elements are of access time for a hard disk?
You've got to rotate the platter into position.
Okay, that's good. So just like elements of access time. You have to rotate the platter into position. That is specifically called rotational latency, because we have to have big words to describe simple simple things. So rotational latency, which is the time to rotate the appropriate block under the read-write head. Okay, and then there's a second measure. Yes. Yes, you have to move the read-write heads to the appropriate track, and that is called seek time. Okay, so that's time to move the read-write heads to the appropriate track. And the read-write heads are also synchronized. You can't move one read-write head to, say, track 10 while moving another read-write head to track 100. They have to all move to the same track. Okay, so they all move. Not only do the platters rotate synchronously, but the read-write heads also go in and out synchronously. So those are the two elements of access time on a hard disk: seek time and rotational latency. And then we come to the combined, so just some numbers from about 2014. So this year you have, so I'm going to say, so we're going to say random access time, which is the time to get to the appropriate head. So random access time equals seek plus rotational latency. So it's the time to get to the appropriate block. And it is roughly 3 milliseconds for a high-end, we'll call it enterprise grade HDD. So HDD is hard disk drive. Just going to abbreviate it as HDD, hard disk drive. It is 9 milliseconds for your average desktop. And it is 12 milliseconds for your average mobile device, which includes laptops. Okay, that includes, so mobile devices includes your laptops. That's pretty slow. Okay, yes.
I don't know if you know this. How does the solid state hard drive stack up?
We're about to get to that. So, in fact, I do know, but just give me a moment, okay? So, this is pretty slow, right? We're used to processors that are several gigahertz, so they can execute generally at least 1 billion instructions a second. So, even in the best case for an enterprise grade hard disk drive, we're talking about 3,000 microseconds. So in the time that you can do one get to one block, you're going to be able to typically execute at least 3,000 instructions. Okay, probably more. So it's very costly to have to stop your program in order to get your data off the disk. The reason I'm emphasizing this fact is because we clearly, therefore, when we design our databases, want to do so in a way that our most heavily used queries will take the least possible, or will load the least possible number of blocks into memory, because each block we have to load is going to slow us down considerably. Once we reach the block, that's not the end of the story. We still have to transfer information off the block. So the transfer rates are about 100. So the transfer rates for a high end, so again, transfer rates for enterprise grade, hard disk drive, is roughly 140 megabytes per second for both reads and writes. So you at least do get a pretty good transfer rate once you're there. Let's see, I'm not always good at this. 4,000 bytes and 140 megabytes. Knock 140 million, 140,000. I think it's roughly like about. Can someone do the math quickly? 4,000 divided by 140 million. Is that like something like 1/1300? It's pretty fast. Okay? I guess the point is most of your time is going to be spent getting to the block. The transfer rate off the block is going to be pretty fast. So the gentleman asked, what's your name again? Isaac. So Isaac asked, what about solid state memory? So solid state memory is kind of the up and coming way that secondary storage is done. I don't know, how many of you have secondary storage on your computers? 1, 2, 3, 4. Much faster, right, than hard disk drives. And so solid state, let me write it down. So solid state devices, basically, they are like random access memory chips, except that they're able to permanently store data. So that's all electronic, whereas a hard disk drive is mechanical. The solid state devices are completely electronic. And they have some way of, again, applying a voltage charge or something and setting the bits, and when you turn off the computer, it maintains them. They're much faster. We'll see that in a moment. Their disadvantage is they're still trying to increase their lifespans. So when they first came out, they had an expected lifespan of a little less than 5 years. And then they fail. From what I understand, the failure rate, the so-called, when you have a hard disk crash, they appear to be more reliable than disk drives, which makes sense, right? You'd expect more of a damage from a mechanical device than from an electronic. But when they go badly. Okay, so it tends to be you don't just lose a sector or a block, you lose more than that. So your crashes tend to be more catastrophic with solid state devices. So the random access time. Okay, remember that was 3 milliseconds for an enterprise grade hard drive. It is less than 0.1 milliseconds for a solid state device. And that's all in seek time because there is no rotational latency. So the random access time for a solid state device is completely seek time, finding the right place that holds it. The transfer rates are actually not as fast as you might think. So it depends on the quality of your SSD, SSD, solid state device. Anywhere from 100 to 600 megabytes per second. I was a little surprised about that. I thought that they compared even more favorably than that, but they certainly, remember, it's not the transfer rates that are killing your hard disk drive or killing your performance with a hard disk drive. It's the random access time, and here solid state devices are the clear winner. That's transfer rates for reads. Okay, for writes, it depends on the bucks you put out for your solid state device. If you're cheap, you can expect it to be about 10 times slower. If you got the deep pockets and went for the good stuff, it's about as fast. So the write times, or write transfer rates, okay, are comparable for high end, comparable to read rates for high end devices. Okay, and 10 times slower, or up to 10 times slower for low-end devices. And I am not a hardware guy, so if you ask me what about the solid-state memory in your laptops, I have zero idea whether those are high-end or low-end. So I don't know what the read-write transfer rates are. Okay, but it is a big difference if you have the cheapo ones. Okay, so even with your solid state devices, 1/10 of a millisecond still is costing you something. And it's likely going forward as they get solid state devices that are more and more reliable, and as the cost point goes down, they're going to become much more common. I imagine eventually they're pretty much going to replace hard disk drives. But even so, there's still the fact that when you go to your secondary storage, which is what both a hard disk drive is and a solid state device, your program is going to stall for some period of time. And our goal is still to minimize the number of blocks of data that we have to read into memory. Okay, so there's two ways that we help minimize the number of blocks and also minimize our seek time. So the first, okay, so our goal is to minimize, I guess, disk access times. Disk access. So the first thing we can do is we can use what's a so-called cluster key to physically organize the records. And by records, I mean tuples. So now I know I've dropped down. I guess, remember early on I said there was a correspondence between relational terminology and files. We had tuples. And now you're going to hear me referring to tuples as records. You're going to hear me referring to relations as files. And you're going to hear me referring to attributes as, someone remember? Fields. You're going to hear me referring to attributes as fields. So it's the way it is. When I start thinking about physical design, I drop down to that terminology. So when I say record, I mean tuple. When I say file, I'm talking about a relation. When I say fields, I'm talking about an attribute. So when I say I'm using a cluster key to physically organize the records, what I mean is I'm choosing one field and I'm going to physically organize my file according to that field. And frequently, the key I use to physically organize my records is not the primary key. Instead, I'm typically going to choose a cluster key or a field that's used in range queries. So usually the cluster key, or the field chosen for the cluster key, I'll put it in parentheses because you might have a secondary key too. Like if I choose last name as my cluster key, I probably will choose first name as my secondary key. So the field or fields chosen as the cluster key are typically used in a range query. And by a range query, what I mean is in SQL where I say between X and Y. That's a range query. I want all the records in a certain range of values. Okay, so when I physically organize the records, say by last name, it means they're physically co-located on the file or on the disk. And typically the blocks will be physically co-located. So if I have, say, some records with BVZ, cat, dog, then typically, if at all possible, right physically adjacent to it will be the continuation, which might be like Dunn and Igor and Fox. So you'll have everything physically together on the disk. So can someone tell me why that is going to help with my disk access times? If I have a range query, like I say, give me the names of everyone in the organization that start with the letter S. Or if it's organized by salary, and I say, give me all people who earn between 10,000 and 20,000. Yes, Isaac.
Ideally, it would be because they'd all be in the same block,
Mm-hmm.
and even if they weren't in the same block, it would be the next block.
Exactly. So I only pay my random access time once. I only have to do the seek and the rotational latency once. And then after that, I can just, boom, read everything in. And typically there will be a number of buffers for your blocks. So it's not, you can read multiple blocks. And so what's happening is in memory, you have multiple what are called buffers for your blocks. This is just conceptual, but it's good enough. So you're reading, say, you read into buffer 1, and while the read into buffer 1 occurs, your program sits and waits. Once buffer 1 is full, it continues and starts to fill buffer 2. So that means that block is coming into buffer 2, but once I've read the BVZ block into buffer 1, it's freed and released to the program. So now the program is able to start processing what's ever in buffer 1 while the read goes into buffer 2. Remember, the reads, even at that fast rate of 140 megabytes per second, there's an excellent chance that before buffer 2 fills, we will have finished our processing on buffer 1. So in fact, there's a good chance that the program will again sit and wait, waiting for buffer 2 to fill. And when it's done with buffer 1, it will release buffer 1, or somehow it will know, the query processor will know to release buffer 1. So then the next block could again start going into buffer 1, and then buffer 2 gets released. So usually you have at least 2 buffers for a file. And that's how you can be assured. Remember, you might have said, why do I know that I don't have to pay the rotational latency more than once? It's because it's just going to, as soon as it finishes with this first block, it's not going to stop reading. It's going to immediately start reading the second block into buffer 2, and then once it finishes with that, it'll probably immediately start reading the third block into buffer 1. So it's not going to incur any more rotational latency. Now, when it's done with the track, and if there is more data to read, now it may incur a slight seek time, right? Because they'll have to move off that track potentially. Potentially have to move off that track. Okay, there's clever ways that you can even, remember I said this platters were sitting on top of one another? There's clever ways of setting it up so the file is striped on the same track. You know what I'm saying? When I say striped, it's like same track on platter 1, platter 2, platter 3, platter 4. So as soon as it comes all the way around, you just start reading that. You started on platter 1, now you just start reading on platter 2, and you don't even incur any seek time to go to a different track. So there's all kinds of super clever things that can be done to minimize the amount of access time and to try to spend as much time as possible just doing your data transfer. Okay, so the cluster key is important because it basically minimizes our random access time. But that only works when we have a query that is a range query. Most of the time we don't have range queries. So most of the time we have things like selections. Give me a person whose salary is equal to 30,000, or give me all rooms in the Grosvenor Hotel, which involves a join on on a primary key and a foreign key. So in that case, it's not likely that the clustering is going to help us. And in that case, we have to use indices. And we have a number, so some terminology first. So we have primary index. We have indices that are called a primary index. And that's the best kind because it means that the file is physically clustered using the primary key. This is not particularly common because most of the times the primary key is an artificial key and it's no good for clustering. So in fact, there's typically not that many files that are physically clustered using the primary key. Like in our hotel database, the hotel number was a artificial key, the guest number was an artificial key, the bookings were not. The bookings, but in truth, there would probably be a booking number making that artificial. And there was a room number. Actually, all the keys were probably artificial in the hotel relation as an example. Okay, the hotel relation would be probably physically clustered on hotel name. The guest one would probably be physically clustered on guest name. The booking would probably be clustered on what? Date from. And the room would probably be clustered. Actually, this one's a bit tricky. It's unusual. So if you can remember, it's not room number that's likely to be clustered on. Right? I mean, the same room number could be in several different hotels. Hotel number is one, and what's the, so hotel number, and what's a likely secondary? Actually, probably not room number. If you're doing room type, the most common query is going to give me all king-size rooms at the Marriott. So it's probably going to be hotel number with a secondary cluster on room type. Okay, so that's where you have to know what's the most common query. Okay, I'm guessing that's the most common query on the room relation, cluster query. Okay, but that's just to show you that in none of the cases, other than the hotel number for the room relation, was it actually clustered on a primary key. Okay, and even on the room relation, the primary key is hotel number, room number. So it was only a partial cluster on the primary key. Okay, so just the point is, it's rare to have a primary index. It's much more common to have what's called a cluster index. Okay, so the file is physically clustered, okay, an index on the key, or on the field, or fields used to physically organize the records. So even if you have the records clustered by, say, last name, you still probably want an index on it because you still want to be able to efficiently find a point query. By a point query, I mean a single records, like give me the guest record whose name is BVZ. You still want a fast way to get at it. You don't want to have to read the file starting at A until we get to BVZ. You might think that's not so bad. Let's search for van der Zanden. Now it's a lot worse because we're at the end of the alphabet. Okay, and the third type of index is the so-called secondary index. It's the most common type of index. It's an index on a non-clustered non-clustered field or fields. Okay, it's the same as attribute or attributes. So an index on a non-clustered attribute or set of attributes. So with an index, basically an index, what it does is like a table of contents. It tells for each attribute value, like say BVZ, it's going to give a disk address. Okay, so it depends how the disk is, but it might be like disk number, say track number, and perhaps block number on the disk, on that track. So it might be, in this case, a triple. It all depends on how the disk is organized. But the point is, the index gives you the attribute value, and then it somehow gives you an address on the disk so that you can then go out and find that particular tuple that contains that value on the disk. So the index is a lot smaller. Oftentimes the index can be held in memory. Not always, but close to being held in memory. And then it's a lot faster to access it. Or even if it's not held in memory, as you'll see, there's ways to organize the indices using hashing so that at most one disk access will locate the index entry, and then a second disk access will get us the block. So we'll see that in a moment. But the general goal with secondary indices, so I'll say goal with a secondary index, is to retrieve a block with at most 2 disk accesses. One to get the appropriate block from the index, and the second to then get the appropriate block for the tuple. Okay, so one for index block, for correct index block. And one for block containing the tuple. Okay, questions about that? Okay, so there are some cute things that you can do with indices. Okay, so cute, I'll call them cute things to do with indices. So this is all kind of hacker stuff, but it's cool. Okay, first thing you can do is you can sometimes use them to solve, okay, sometimes you can answer a query by consulting only the index. Okay, this is especially true for aggregate queries. Okay, so this is especially true. So if I say I want the average salary for all staff in a branch, I should be able to get that off of an index. I shouldn't have to go, well, that's actually not true. If it's for a specific branch, it's only going to work if my index is both branch number and salary. So I'll modify that. I'll say, let's say I have a query that says, give me the average of all staff, average salary of all staff in the organization. That could be done with just an index if there was an index on salary. Okay. Or if you did have an index doesn't have to be on a single attribute. It can be on multiple attributes. So if it so happened that your index was on both the branch number and the salary, then you could even answer a query that said, give me the average salary for each branch. So this is, I'm just going to say, especially true for aggregate queries. Okay, another thing that you can do, this gets a lot more complicated, but you might actually not store the value in the tuple, but only in the index. So if you had, for example, an attribute value that occurs a lot, like say king-sized room, instead of putting king, now I understand you'd probably use an integer code to represent it rather than the full string, but I'm just giving a for example. You might have a way of just putting the values in the index like king-sized room, and it points to all tuples that contain it, and some of your, it's going to make some queries expensive, like when you have to answer a query by just reading a block and you want to know what that field value is, you can't get it. You'd have to go back to the index. But sometimes you may very rarely need the value physically in the tuple. You may be able, most of the queries go through the index, in which case you wouldn't have to store the value in the tuple. It's not necessarily physically stored in the tuple. You could just store the value in the index. Like if all my queries on the room relation are of the form, give me all rooms at the Marriott that are king-sized, you only need the index. You don't need to physically store the room type in the tuple. Okay, this is esoteric. Not saying that this strategy works a lot or pays off a lot, but this is the levels to which you will stoop to try to save storage and to try to save disk access times. Because anything you can do to reduce storage and to reduce your disk access times, you will do, because it's so much slower than doing stuff in the CPU. Okay, and that's why I called it cute things. I'm not saying you do this a lot. It's just stuff that you can do with them. Okay. Okay, so considerations in choosing an index, because not everything should be indexed. Okay, so there's both do's and don'ts. Okay, we will start with do's. Okay, so we'll call them the do's. Okay, so you almost always index the primary key, which I call PK. Okay, even if it's not the cluster key. Why? Can someone tell me why? Why do you index the primary key? I will give you a big hint. You also index foreign keys. For what? What kind of data in particular? What kind of query? Joins. You are performing joins on the primary key and the foreign keys all the time. Hence, it is a very good chance that your primary key and your foreign keys are going to be hit a lot, and you will be wanting to index them. Okay? Then index any attribute that is heavily used in queries or heavily accessed by queries. In, I'll say, the where clause. Okay, so date 2 is a good example of that in the booking relation. It's not a foreign key, it's not a cluster key, but believe me, we frequently need to know what is the checkout date for our customers. So a good example of an attribute that's going to be heavily accessed in the where clause of queries is going to be the date 2 in the booking relation. Okay, then index attributes that are, this is kind of repetitive, I understand, but index attributes involved in well, I actually covered it. So I'm going to write selection or join, but I covered that with A, B, and C, really. Okay, because joins are typically done on foreign keys and primary keys, and 3 handled the selection, index any attribute that's heavily accessed in the where clause of query. So I feel like I hit already that one. Next one is used in order by or group by or anything involving sorting. Such as union or distinct. Because union involves sorting. Why does union involve sorting? A union, 2 relations together. Why is sorting important in a union? Got to get rid of duplicates. Okay, so the fastest way to get rid of duplicates is to have 2 sorted files and just do a linear scan. If they're unordered, every tuple you're going to have to scan the other one to figure out whether it's there, right? So in one case, you make 1 pass through the files. In the other case, you make n passes, essentially. It's the difference between order n and order n squared. Okay, distinct should be pretty clear. Is if I'm getting rid of duplicate tuples, it's better to have them sorted. Okay, if I'm doing a group by, so I frequently do a query that says give me the number of staff in each branch. Well, it would be good to have an index where the branch is, well, where the branch numbers, let's see, go back, do this again. Regroup, yes. If I'm ordering by, if I group by branch number and it's not, now I understand branch number has probably already been indexed because it's a primary key. But if it hadn't been, then you would want to index it because you would want to be able to quickly get all tuples associated with each branch. Okay. So next one is index attributes used by built-in functions. Particularly the aggregate functions. Okay, because as I said earlier, you can probably get a index-only plan. Okay, an index, when I talk about a plan, the query optimizer develops a plan to satisfy your query. It's how it's going to go about accessing the tuples that need to be done. Like, is it going to do a subquery first and form an intermediate relation, is it going to do a project first and eliminate all tuples that, or I'm sorry, a project where it eliminates unnecessary columns? Is it going to satisfy the where clause first? It has to figure out what's it going to do first. Project first, select first, do a join first, do a Cartesian product. It has to figure out what the order of operations is. That's a plan. So an index-only plan is one that involves only indices. You don't have to go to the tuples. So that's the last one in the do's, is also index attributes. Attributes that could result in an index-only plan. Okay, so there might be some queries that you figure are going to be frequently performed but not on aggregate operations. And you want to do that. So maybe a common operation on a room thing would be to give me all rooms at a hotel of a certain type. That's 3 attributes, but it might be a small subset of the attributes in the room relation. In that case, you might consider creating an index on those 3 particular attributes, because then you could actually satisfy the query, give me all rooms at the Marriott that are king size, give me all the room numbers of all rooms at the Marriott that are king sized. You could do that with an index-only plan. That's an example. So those are the do's. Okay? There's also some don'ts. You don't want to index everything. Okay? If you indexed everything, first of all, you double the size of your database. Plus, you actually give the query optimizer has to consider different combinations of indices. So if you give it a whole bunch of indices to work with, you start to get exponentially increasing the number of ways it can combine indices to get a plan. So you can quickly overwhelm the query optimizer. In fact, you could slow it down. So don'ts. Okay. So do not index small relations. It's a waste of time. Okay, and that's going to depend, but like if you, a good possibility is our branch relation. Even in a pretty big organization, the total number of branches is not going to be huge, and there's a good chance that indexing it is not going to be any good. Okay, we already said that with an index, we're trying to hold it to 2 disk accesses. So if your relation is 2 blocks or less, you certainly wouldn't want to index it. But even at 3 or 4 blocks, it's not clear that it's worth an index. You can get it pretty fast anyhow. Okay, so don't index small relations. Okay, 2 is avoid indexing frequently updated attributes. That should be pretty obvious, because if you are frequently updating an attribute, it means you will also have to frequently update the index. In fact, any index involving that attribute. So that's going to at least double your update time, because indices are also kept on disk. So every time you update a tuple containing that attribute, you'll also have to update the index. That'll be a second disk access. That'll slow you down. Okay, avoid indexing attributes if the query will retrieve a significant proportion of the relation. So avoid indexing attributes if the queries on those attributes typically return a large proportion of the relation. And this is where it can get surprising. So 1%, returning 1% of the relation sounds like a pretty small proportion of the relation, right? That is almost certainly way too big for indexing. Here's why. Remember I said that a block in Unix is roughly 4,096 bytes. Let's say your records are 40 bytes. Okay? That means roughly 100 records per block. Okay? I just told you the query returns roughly 1% of the file or of the relation. That sounds small, right? But on average, you're returning 1 record per block. Whoops. 1 record per block on average means you return every single block in the relation. No good. Okay, if it's random. Now, if it's clustered, that's totally different. But if it's random because it's not physically clustered on that attribute, that means the tuples are scattered randomly over the entire relation. And you're returning 1% of the relation. So because it's randomly distributed, you'd expect roughly 1 record on each block to be returned, meaning you're returning every block in the relation anyhow, so you just wasted your time. You might as well have just read through the entire relation. So the way that you actually phrase that to make it more objective is that, okay, so I'm going to say 3A here. What that means is that you want the expected number of records per block to be much, much less than 1. That less than means much, much less than 1. We're not even talking like 0.5. At 0.5, we're still looking at accessing half the file. Okay, we're talking about like ratios of 0.01. So that's records per block. So that's actually now down to like 1/100th of a percent. That's what I mean by tiny. And that's what I mean by much, much less than 1. I'm not talking about a half or a quarter or even 1/10, because that's still returning a big chunk of the file. We're talking small, like 0.01. Okay? And then the last one is avoid indexing attributes that consist of long character strings. And the classic example of that is street addresses. So I'm just in parentheses, the classic example is street addresses. They're not typically used. You don't typically search by street address. I know Google being a big exception. Obviously, Google Maps does. So they might actually decide to index by character strings. But in general, you don't index attributes that consist of long character strings because they suck up a lot of storage. Okay? it's very good chance that the street address is going to be more than half the number of bytes in your tuple. So if you index the street address, you probably just added 50% storage to your database in that one index alone. Okay, so these are rules of thumb. They're not absolute. Okay, like I said, Google Maps almost certainly violates rule 4 because most of your accesses on Google are to street addresses. And you'll notice that they conflict. Okay, there's quite possible, especially number 2, there's a good chance that some of your attributes that are prime candidates for indexing are also frequently updated. So it's one of those things where you just have to weigh the costs and benefits. Now, I could rant about the rest of chapter 18 in the book because it talks about transactions analysis. Here's my pithy advice on transaction analysis, which is it's complicated, it's unlikely to really work, so the best thing to do is concentrate on a few queries that you think will be most heavily used, and then tune when you get the database working. So make your initial selection of indices based on the queries that you think will be most frequently used, and then tune based on actual performance. Okay, because there are literally dozens of queries that people will probably want to perform on your database, and if you take them all into account, you probably will end up wanting to put an index on almost every attribute, which is a disaster. So that's my advice, is pretty much ignore all the claptrap in chapter 18 about transaction analysis. Instead, just look at a few queries that are likely to be frequently used and then tune based on actual performance, which is what I will expect you to do on the 5th homework assignment. There's a problem in there that asks you to decide which indices you should put on the different relations in the hotel database. And if you manage to come up with an answer that puts indices on every attribute of every relation and you argue convincingly for doing so, you will get 0, because I can tell you that there should not be indices on every attribute. Okay? So next time, we're pretty much done today. Next time, we are going to talk about B-trees and extendable hashing. If you can, try to look at Appendix F, which I think, no, not every one of you is going to have, because if I'm not mistaken, it's on the DVD that accompanies the book. I will see if I can't get copies from a data structures textbook for next time that I can hand out in class that gives a good description of B-trees and extendable hashing. So at any rate, Tuesday we're going to go through B-trees and extendable hashing, and that will finish it up for databases. Remember, you got a homework assignment due tonight at 11:59 p.m.